Aloha, Richard Halverson here. This is ICS211, and today this video, I'm gonna talk about trees, starting with this binary search tree search algorithm. Let me share my screen. Okay, in this video, I'm gonna try to get through 19.4, 19.5, and 19.6. So we're talking about binary search trees, and with the binary search tree, you can it's easy to search for things because uh, what you're searching for is either if the node exists in the tree with the key value that you're looking for, you start at the top and it's either that node, or if what you're looking for is less than where you are, you go to the left, you go down the left subtree. If what you're looking for is greater than where you are at, you go right down the right subtree, and you keep on doing this until you either find it, or you learn that it's not there. So the search algorithm, given a key, a search algorithm returns the first node found matching that key, or it returns null if the matching node is not found. So this is the algorithm. While the current node is not null, if the key is equal to the key value of the current node, then you return the current node. Otherwise, if the key value is less, the key value that you're looking for is less than the key value at the current node, then you traverse down the left. You go down to the left child of the current node. Otherwise, you go down the right child of the current node. Here's a simple challenge already. Let's see, let's do it. So what does binary search tree this return? It's going to return 96, I guess. Returns the current value. Okay, so I'm going to say, let's start it up. Okay, let's do this one. In searching for 72, which nodes are visited? Enter the nodes in order. We're searching for 72. Okay, so first we're going to visit 66. And then we're going to visit, what we're looking for is bigger than 66. So we go to the right and we look at this one, 72. And that's the one we're looking for. And that's as far as we go. What is returned? Node 72. Is that right? Oh my goodness, it's that easy. All right, let's look at the insert algorithm. Given a new node, a binary search tree insert operation inserts the new node in a proper location, obeying the BST ordering property. Okay, so we have a tree and we have a node we're going to insert. And the first thing we check to see is if the tree's root is null, then it's an empty tree. And so the node is going to simply be the root of the tree. So the tree root is equal to the node. Otherwise, the tree root is not null. So the current node is equal to the root of the tree. And then now we're going to search down the tree to find the first empty spot to put this new node in. And so while the current node is not null, the key value of, if the key value of this node is less than the current node's key value, then we go down the left. Then we look to the left, and if the current node's left pointer is null, in other words, if there's no left child at the current node, then that's where we can put this new node. So we attach it there. And we set the current node equal to null. And that's gonna that will make it so the next time we come around, the while loop will end. The while loop will end. So this is the the ending condition. All right. And so if the current node if it's not null, that means we have to keep on if the current node left child is not null, then let's traverse down it. Let's move the current node to the left child. That's if the current node, the left child of the current node is not null. Let's see if the now if the node that we want to insert is not less than the key at the current node, if it's, in other words, if it's greater than or equal to, then it does this, and that means that the new node could go on the right, should go on the right. If the right child of the current node is null, then we have a spot for it, and we attach that node there, and we set the current node equal to null, so it'll terminate. The while loop will terminate. Otherwise, we traverse down the right node, and we keep on either traversing down the left or the right. No, we keep on traversing down the left node if the current node is greater than the one we're trying to insert, or we traverse down the right child, the right subtree, if the current node is less than the node that we're trying to insert, until we find an open spot. All right. So let's try this challenge activity. Insert algorithm. Okay, with the first, where will the new node 42 be inserted? The new node 42 would be inserted right. We go down, should be to the right. So there's a node there, and so it would be to the left of this one, and there's no node there, so we can insert the 42 here. All right, let's start it out. Let's do a more difficult one. Let's do this one. Let's do this last one here. Okay. When inserting a new node with the key 4, which nodes are visited? Enter nodes in order visited. Okay, we start here, and we want to insert a 4, so that's going to be to the left. So we go down here, go to the left. Oh, there's a node there, so let's go here. And then we would 4 is less than 10, so we would go to the left, and there's no node there, so the 4 would go right here, it looks like. 4 would go right here. So first we visit the 20, and then we visit 10. Is the node added as a left or right child? Why, it's added as a left child. So it would go right here. That's what I think. Check. Ah, yes. All right, very good. Now let's take a look at the remove algorithm. The remove algorithm is the most difficult. We have to look at each case of whether it's got a left child, whether the current node has a left child, or the current node has a right child, or the current node has both, or neither. Okay, so given a key to remove, the binary search tree remove operation removes the first found matching node, restructuring the tree to preserve the binary search tree ordering property. So that's the tough part. It's you find the node that you want to remove, you remove it, but then you got to restructure the tree to preserve this ordering property. So if we have a tree like this and we want to remove the 25, that's easy. 25's got no children, we just remove it. Okay, here if we want to remove the 25, well, it's not quite as difficult, but we just take it. It just has one child. So we could take that child and put it up in its place, whether it's the left child or the right child, or whether it has just a left child or it has just a right child. We can just put that child up into the place of the node that we're removing. So here, when we remove the 25, it's going to end up looking like this with the 30 up in the 25 position. All right, so that's removing when the node just has one child, single child. Now, when removing an internal node is a little bit different. Let's say we want to remove 25. So to remove 25, we actually have to go and find the successor node. Okay, we learned about successor node back up in here. Yes. So anyway, so 25, the successor node to 25 is this one. That's the next one in line. So we copy this data and put it up there. That's all. See, so this gets put up there. So we can click through this. You should click through all these. So we take a copy. This is the current. We find the successor node. It's this one. We want to remove 25. Find the successor node. It's that one. And then we copy that data up into there. And then we get rid of that one. All right, so that's how we remove. This is the BST remove algorithm. Kind of complicated. If the current key is if the node is found, then and the left child of the current node is null, and the right child of the current node is null. That means it's just a leaf node. You can just yank it out, no problem. If it's a root, then you end up with an empty tree. If the current node that you're looking at, if the right child is null, that means the left child is not null, because if they were both null, they would be taken care of here. This is if they're both null, if both children are null. Here we have the right child is null, but the left child is not null. Then we take the current left child, and that ends up replacing the node that we want to remove, the current left child. If the current left child is null, but the right child is not null, then the right child is the one that replaces the node that we want to remove. And if the node we want to remove, if it has two children, then we have to find the successor node. And so here we loop, we go down the right, and then we go as far left as we can go until we find the successor node. We copy the successor node data, and that's how we replace. We put that data into the node that we're removing, and then that node is removed. All right. So that's the remove algorithm. Let's do one of these here. Let's see. So here, when 10, removing 10, that's just going to be, this gets removed, and we end up with what's the left child of 20 is going to be null. The right child of 20 is going to be null. It's no big deal. Let's do a more difficult one. I'm going to do this one. I'll do this one. All right. What is node 40's successor? Well, it would be 50. Wow, we can remove 40. Node 50 is the successor. Now, when we remove 40, what happens? The successor goes up there. So now 50 is going to be here. What is node 40's successor's left child? It's going to be 20. methinks. If the 50 goes up to here, then that means the left child of 50 is now going to be 20, I think. And the right child of 50 is still going to be 60. So if we remove 40, then the 50 goes up here, and the 20 is now the left child of the 50, and the 60 is still the right child of the 50. That's what I think. Is that right? Very good. All right, that covers sections 19.4, 19.5, 19.6. And in the next video, we're gonna cover next video we're gonna cover 19.7 and 19.8 and 19.9. I think we're gonna probably go all the way because you have to learn in order and height to be able to do the next lab. And so that's what's going to be covered in the next video. Anyway, so in this video, we covered 19.4, 19.5, 19.6, and got you through the challenge activities. And that's it for this video. Thanks for watching.